Welcome to MyProjectBazaar.com. Let me discuss about the process outage constraint robust transmission optimization for multi-user MISO downlinks tractable approximation by conic optimization. Let me discuss about the abstract of the project. This paper considers robust transmit beamforming for multi-user, multi-input, single-output downlink transmission where imperfect channel state information is assumed at the base station. The imperfect CSI is captured by the moment-based random error model, in which the BS knows only the mean and covariance of each CSI error, but not the exact distribution. Under this error model, we formulate a distributionally robust beamforming problem in which the total transmit power at the BS is to be minimized, while each user's SINR outage probability evaluated with respect to any distribution with the given mean and covariance is kept below a given threshold. The system developed three convex restriction methods for robust outage constraint transmit optimization. Under the multi-user MISO downlink scenario, simulation results were provided to illustrate the performance accuracies of the proposed method. In this technical report, we further demonstrate the efficacy of the proposed methods by showing more simulation results. In particular, we illustrate the applications of the proposed methods to the max-min fairness formulation and the achievable rate region characterization problem, which was not considered owing to the limit of space. This technical report serves to provide further simulation results for this paper, outage constraint, robust transmit optimization for multi-user MISO downlinks, tractable approximation by conic optimization. In addition to the rate constraint formulation, which is the main focus of the aforementioned main manuscript, demonstrate how the proposed methods can be used to tackle the max-min fairness formulation and the achievable rate region characterization problem. Let me discuss about the flow diagram for our process. First, initially, the imperfect channel state information has been taken. Next, we have to design MISO downlink network. For convex restriction formulation, it usually yield rank 1 solutions. Thus, the obtained rank 1 solutions can be used to directly as safe approximate solution to the beamforming problem without the need of Gaussian randomization procedure. This suggests that beamforming could be an optimal transceiver scheme for the convex restriction formulation, since the convex restriction approach proposed in the previous section entails finding convex upper bounds on the violation probability. Next, the sphere bounding approach. It has long known that the probabilistic constraint can be approximated in a conservative fashion using robust optimization techniques, although its application to the multi-user MISO downlink scenario has not been explicitly considered. Let us concisely review the idea here. Consider an arbitrary set. Next, in the Bernstein type inequality, it has long known that the probabilistic constraint can be approximated in a conservative fashion using the robust optimization techniques, although its application to the multi-user MISO downlink scenario has not been explicitly considered. Next, the decomposition based large deviation inequality. Although the convex restriction derived using methods 1 and 2 can be formulated as semi-definite problems, that is SDP, and hence are polynomial time solvable, they can still be expensive to solve in practice if the size of the LMI constraint is large. Thus, it is of interest to develop convex restriction that involve simple convex conic constraints such as SOC constraints. In this subsection, propose yet another convex restriction method that has such a property. This method is based on the following large deviation inequality for complex Gaussian quadratic forms. Finally, the performance has been analyzed. Finally, we obtained the rate outage constraint problem. Based on that rate outage constraint problem, we analyze the performance. System present three tractable convex restriction formulation of the rate outage constraint problem. This naturally leads to the questions about the relative performance of this formulation in the following subsection. This question by comparing their computational complexity as well as their tightness in approximating the original rate outage constraint problem. Let me discuss about the running procedure for our process. Select the main.m file in the current folder, write the file and run for executing this process. Here we obtain the performance results for our three methods. This is the input signal values, and this is the channel coefficient H values, and this is the received signal we obtain, and this is the achievable rate. This is the feasibility rate for our three methods and also our existing probabilistic SOCPL methods by varying the gamma value. This is the average transmission power for our three methods, three constraint problems, and also our existing probabilistic SOCP algorithm. This is the feasibility rate by varying the gamma value for our methods, three constraints methods. This is also the average transmission power by varying the gamma value. Here also we are compare the result with our three proposed methods and also existing methods, that is probabilistic SOCP algorithm. Totally we analyze the three constraint problem for our input signal. Thank you.